So we are ready to go. So let's get started on today's class. What we're going to be doing today is we are going to be continuing our look at problem solving and creativity. So this is problem solving and creativity part 2. And what we're going to be, actually no, this is problem solving and creativity part 3. And what we're going to be looking at today, because we're happy that we're at part 3, is how do we navigate the problem space idea that we came up with in the last class, and how do we work a problem set, work through it, make the choices that we make for each of the operators. So what we're going to work on, or work on the idea, is that we have a mind that tries to work well and sometimes doesn't, but we have a mind that searches a problem space when it's trying to solve a problem and tries to find that solution, find that way through by searching through the space and what are the allowed moves in order that you can finally get to that solution. So that's what we're going to be working on and taking a look at today. So at the beginning of this class, for the first part of the class, we're going to go through a quick recap of the information processing approach. Then we're going to take a look at operator selection. How do we navigate through a problem space using backup avoidance? And then we're going to take a look at why that makes insight problems so very difficult to solve. So just a recap on the information processing approach. So this is a way of representing problem solving using information states and using information processing rules. So we illustrated it with the Tower of Hanoi problem, but basically the idea is that in any problem that you're solving, you have your initial state. And the initial state is the representation of the problem at the beginning of the problem. This is where you start from. So if you remember that basic definition of a problem, you have a start state, you have a goal state, there's an obstacle between where you are and where you want to be. Where you are, that is the initial state, that is your start state. So in the Tower of Hanoi example, it is represented as having all the disks stacked on that first position. You then also have your goal state. And your goal state is when you finally attain the solution to your problem. That is your goal. And in the Tower of Hanoi, it is having all your disks stacked onto another position in the problem. And then the last portion of these states, or the last type of state, are intermediate states. And these are the states that you traverse through or encounter possibly on your way to the goal. So they are where you are when you are working on the solution, when you've made progress, but you haven't quite made it to the end state. The intermediate state is where you end up as you are moving towards your goal. And then the different states can be organized into a problem space, which shows all the various states of the problem, but importantly also shows the relations between the states. Because the last component of this is the idea of an operator. And an operator is a technical information processing term that means the way that you are able to move between states in your problem space. So for example, in the Tower of Hanoi, it is the rules of the problem that you can only move one disk at a time, and that a larger disk cannot be placed on top of a smaller disk. Those are the operators, the ways that you can move between those states in that problem space. And if you put all these components together, you can create what is known as a problem space. And again, that shows all the relations between the initial state, the goal state, and all the intermediate states. And solving the problem is finding a path through that problem state from the initial state to the goal state. Yep.
So the intermediate state is only the green circles, not anything else?
No, in this example here, the intermediate states are everything besides the initial state and the goal state. And then the green circles is one possible path from the initial state to the goal state. So if you were looking at this problem space and you thought to yourself, well, what is a solution to this problem? basically the outlining of all those states that are in green with the arrows. Those are the operators also in green. That is one potential solution to the Tower of Hanoi problem. And if you were navigating, as we're going to see, through a problem space, you have to discover this path. And if you get stuck on this problem, oftentimes it's because you've gone down a incorrect pathway in the problem space, and then you have to deal with the fact that you are not where you need to be to traverse and solve this problem space. All right, and then we introduced the hobbits and orcs problem last time, where you have 3 hobbits and 3 orcs on one side of a river, and there's a boat on that side of the river, and the boat can hold at most 2 individuals. And your goal in this problem is to get the hobbits and the orcs from one side of the river to the other side of the river. And the operator is basically how the boat works, that the boat can at most carry 2 people, has to carry 1 person in order for the boat to be to cross the river, and also that at no point in this problem can the orcs outnumber the hobbits on either side of the river. So at no point are you allowed to have only 1 hobbit and 2 orcs on one side of the river. If that happens, then the hobbit will get murdered and you will fail to solve the problem. So we had our initial state, we have our goal state, and this problem is actually a riddle because it is very challenging to solve. So the question now becomes, well, why is this problem challenging to solve? What makes it not immediately obvious how to get around the obstacle? And as we saw last time, the really perplexing part of why this problem is difficult to solve in terms of the problem space approach is the fact that in reality, there's only one choice to be made in this entire problem solving solution, and that is the first choice. Really, the only thing that you can do is figure out, or the only choice that you have is to figure out who goes across first. And as soon as you come upon the correct solution of, okay, I'm going to send 1 hobbit and 1 orc, we're going to put them in the boat, we're going to send them across. Once you make that move, because of the restrictions of the operators, because of the restrictions of you need at least 1 person in the boat for it to cross the river, and at no point can the orcs outnumber the hobbits, every single step after that initial choice is the only possible step. So this is a problem space that is literally a fork in the road for the first choice, and then just a hallway for the rest of the solution. So as long as you make that first correct decision, you would imagine that the rest of the solution would be rather straightforward because you can only ever do that one move that is the next move to be made. However, this problem is a problem for a reason. It's a riddle for a reason because it does get challenging. And insightfully, it gets challenging in one particular area. So what is it that makes this problem difficult to solve? Well, it stems from the fact that when we have a problem space, such as this, we don't have the entire problem space represented in our minds. So we don't have all the moves already planned out and represented and available in our working memory, for example. We don't have, if you're doing the Tower of Hanoi, you don't take a look at the Tower of Hanoi and mentally look at it and say, oh, okay, 8 moves and I'm done. And I know exactly what those 8 moves are. And then you do the 8 moves. It's more like an exploratory searching of the problem space. So the problem space isn't laid out in your mind like this. It's more laid out in your mind like this. Like you know there's a problem space and you know there are rules that you need to follow, but you don't exactly have the entire thing mapped out in your mind where you can just follow through and find that particular solution. So what we do is we start with the initial state and you start thinking to yourself, okay, well, what can I do here? Well, I can send 1 orc across. But if I send 1 orc across, then I'm going to have to send 1 orc back, and I'm back to the beginning, so that's no good. I can send 2 orcs across. If I send 2 orcs across, then maybe I can work something there. Or I can send 1 orc, and I can send 1 hobbit across. So basically you're reasoning from your first initial state and trying to apply operators and trying to figure out which operators are probably going to work the best. So let's say that you do make that decision and you go with that center choice. You send one hobbit and you send one orc across. From there, unknowns to you, there's only really, well, maybe not unknowns to you at this point. From there, there's only one move that you can do because you can't send the orc back. Because if you send the orc back, then the hobbits will be outnumbered on the upper side of the river, and that's not allowed. So the only thing you can do is you send the hobbit back. That's the only move that's possible. So from there, you make that one move that's possible, and now you have more decisions to make. And again, you just navigate through this kind of where you are and where you can go. But again, on this next decision, you have to send 2 individuals across. You can't send 2 hobbits. Otherwise, that lone hobbit will be outnumbered on the original side of the river. You can't send a hobbit and an orc, because if you do that, then the hobbit that crossed the river will be outnumbered when they get to the other side, so he'll get eaten. So you have to send 2 orcs, and you just continue to try to solve this problem. And in this case, it's, again, weird that it gets difficult because you're doing the only thing that you are able to do at each step of this solution. So what happens? Why does this get to be difficult? The reason that it gets to be difficult is one of the strategies that our minds use in order to navigate this problem space. And that strategy is known as backup avoidance. So we're not entirely sure what the correct solution is. So we use strategies that increase our probability of getting to that correct solution. And one of the big strategies that we use is known as backup avoidance. And that's where you do not select an operator that undoes the effect of previous operators. So basically, you don't undo your moves. So in this Tower of Hanoi example, if we start up there on the initial state that is circled in the green circle, and then we make the move using the green arrow operator, and then we make another move using that green arrow operator. Once we get to that intermediate state with the 2 discs in the first position and the 1 disc on the third position, we do not choose the red operator, because the red operator will take us back to the beginning. And that is something that we as problem solvers just do not like to do. It's sort of a strategy that our mind blocks from us. And in this case, it would be the completely wrong thing to do, because now you're 3 moves in and you're exactly where you started before. So we just have this built-in strategy that we use in problem solving that works most of the time, known as backup avoidance. Don't select an operator that undoes the effect of what you've been doing so far. So how does this explain what is going on with the hobbits? Well, it explains what's going on with the hobbit and orc problem, because in the hobbit and orc problem, we are applying operators that continually move us closer to our goal. So we are continually reducing the difference between where we are, where we start, nobody on the other side of the river, and where we want to end up, everybody on the other side of the river. We continue to reduce the difference between those 2 states. So this is known, again, as difference reduction. You select that operator that most reduces the difference between your current state and your goal. That is, again, a strategy that we have where we take a look at the difference between where we are and where we want to be, and we ask ourselves, what move will make the biggest change towards our goal? And we tend to choose that choice. And as we're going to see, that backfires when we're trying to solve the hobbit problem. So let's take a look at this idea of this difference reduction. Let's take a look at this idea of backup avoidance. And then also, just as a spoiler alert, you're also going to see mental set effects here as well. So keep your eyes open for that. But let's start off with this graph here. So what we have here is we have your x-axis there, and that shows your moves. And we got your y-axis there, and that shows what amount of your goal have you achieved. So that top left representation, that is your initial state, where you have 3 hobbits and 3 orcs and 1 boat all on one side of the river. And in that case, the amount of goal that we have solved is 0. So we got this little circle right down here, and we have solved none of the problem. We are nowhere near getting to the solution, which is 6 mystical beings on the other side of the river. However, when we do that first move, the amount of gold that we achieve is now 2 out of 6. Because we have taken a hobbit and we have taken an orc and we have moved them to the other side. So the solution, we're not there yet, but we know we're closer, right? We've made progress. We've reduced the difference between our initial state and our goal state. And what's more is we've reduced it by the maximum amount that we can. We have made the biggest reduction in our in solving our problem. So that's a good first move, right? We've taken a chunk out of this. We're 2 out of 6 mystical beings on the way there. So now we got to send the boat back. And backup avoidance is one of the reasons why we don't say, oh, okay, to send that boat back, let's put a hobbit in there and the orc, and they can both go back. Because if you do that, if you send 2 people back, you basically undone what you just accomplished. So we're not going to do that. And instead, what we're going to do is we're going to send 1 person back. So you pick yourself a hobbit, hobbit goes into the boat, crosses back over to the other side of the river. And now notice we've gone from 2 out of 6 on the goal side of the river. And now we only got 1 out of 6. So we have had to back up a little bit, but definitely not 2 steps back. So we took 2 steps forward, we took 1 step back, and this is gotten us 1 out of 6 towards our goal. But importantly, it allows us to use that heuristic of maximal difference reduction and undoing what we previously did. So now we have 1 orc on the goal side of the river, everybody else is on the initial side, and now we take 2 orcs and we load them into the boat and we bring them off to the other side of the river. So we have now this situation right here. And now we got 3 out of 6 mystical beings on the other side of the river. So now we're halfway to our goal. And once again, we started from only 1 out of 6 on one side, on the goal side, to 3 out of 6. We have changed. We have reduced the difference by 2 beings. We've reduced the difference by the maximum amount possible. And now we've made it closer to our goal. So we sent 2 people across, and now we're going to avoid backup. We're not going to undo what we just did. We're only going to send 1 person back. And now we're in a position where we send 1 orc back. So now we have 2 on the goal side, 4 on the initial side, and we're making progress. Next move, we're going to take 2 hobbits, and we're going to move 2 hobbits to the other side of the river. So we load up 2 hobbits in the boat. Now we have 4 beings on the other side of the river. We're 4 out of 6 mythical beings towards the goal. We're almost there. We're getting to the point where we can solve this problem. And this is the point where most people run into problems or run into challenges when they're trying to solve this problem. They get to this point in the solution, and then all of a sudden they get stuck. And the reason that they get stuck is because the only move that you can do for the next one is to take 2 entities back across. So the only thing that you can do is you can load up a hobbit and you can load up an orc and you take both of them back across. Because if you send just 1 hobbit, then the hobbit on the goal side, if you send one of these hobbits back across, then the hobbit that's left is going to get eaten by the 2 orcs. But if you send 1 orc back, then the hobbit that is on the initial side is going to get eaten by those 2 orcs. So you're stuck. You can't send back 1 hobbit. You can't send back 1 orc. The only thing that you can do is you can send back a hobbit and an orc. But look what that did to our problem space. Look what it did to where we were getting to our amount of gold. It brought us back 2 steps. So it undid what we had just accomplished, and it violated that idea of backup avoidance. But once you get past that point, then you can take 2 mystical beings across to the other side, and then you can send 1 back, and then you send 2 across, then you send one back, and then you send two across, and you finally solved the problem. So we have this problem set here, and it's difficult. This is a riddle that is challenging because of that one move there. And that move is difficult for us, for our minds to navigate, for our minds to find, because we are working with representations and strategies that want to avoid doing that move. We want to avoid sending back two people when we just brought two people across because of that idea of backup avoidance. All right, so we don't want to select that operator that undoes the effect of the previous operators. And then also, one of the other issues with this solution is that you also fall prey. One of the reasons this is challenging is because you also fall prey to the idea of a mental set. So can anybody point out the mental set that you fall into in this solution? So a mental set is when you continue to use the same strategy to solve a problem over and over and over again because it worked previously, and you kind of get trapped into that solution. So the example that we had was the eggs in the basket, where the first person takes an egg out of the basket, second person takes an egg out of the basket, third person takes an egg out of the basket, and that blocks you from realizing that the last person took the basket. Yep. Exactly. So the mental set that we fall into can be summarized, or the strategy that we fall into because of mental sets can be summarized as bring two across, send one back. And this works in the early going. So in the early going, you're like, hey, you know what? Bring two across, send one back. That's great. I've made progress. Next one, send two across, bring one back. That's great. I've made progress. So now you've had two successful applications of this particular strategy. And now you're like, okay, let's keep going. Send two across. That looks great. Send one back, and you're stuck. So again, you fall into that problem of a mental set where your strategies before have been successful, but now that strategy can no longer be applied. So not only do we have backup avoidance, but we also have that mental set interfering with realizing what is, again, the only possible move: take an orc, take a hobbit, and bring them back across. All right. So again, one last kind of reason that this is difficult to solve has to do with, again, how this problem space is represented. So we do not have the entire problem space represented in our minds. So when we get to this portion here of the problem space where we've just brought across two hobbits, and we have two hobbits on the goal side, two orcs on the goal side, the only possible move that we can do is, again, to bring back one hobbit, one orc. The reason this is challenging and not immediately apparent is because we don't have this entire problem space represented. So we're not sure if that is the only choice. So when we are presented with this, we might think to ourselves, well, we got to do something. So maybe we can bring a hobbit across. No, that doesn't work. Maybe we can bring an orc across. No, that doesn't work. You would think that the next idea would be, well, maybe we can bring back a hobbit and an orc, or maybe two orcs, or maybe two hobbits, whatever the case may be. But again, we don't know exactly what the problem space looks like. So it's hard to know when we don't have those possibilities, when we run out of those possible solutions. All right, so this brings us back now that we have this idea of a problem space and how knowing the relations between initial states, goal states, and intermediate states can help us to solve not only help us to solve the problem, but understand why certain problems are difficult. We are now going to apply this idea to insight problems. And insight problems, again, are these special class of problems where people are aware that they are unaware that they are close to a solution. And mostly it's because it often requires only one step. So the example that we gave, or two examples we gave last time, the haystack was important because the cloth ripped. So why did the cloth ripping make the haystack important? None of us could come up with the correct answer to that. But once you see that the cloth is actually the cloth of a parachute, then all of a sudden it's immediately apparent the solution is there, and it makes complete sense. We also took a look at the funeral problem, about the funeral where this woman meets this incredible man at her mother's funeral, but doesn't get his phone number, doesn't get his contact information. Nobody knows who he was. So a week later, with no way to contact him, she murders her sister. And the question is, why did she kill her sister? And again, none of us could come up with that solution. We came up with a lot of plausible ideas. We came up with a lot of plausible possibilities. But the reason of why did she kill the sister, namely that she was hoping that if he showed up to one family funeral, he would show up to the next, made sense once you heard the answer, but again, was very difficult to get to that point. So again, these problems might seem like they should be super simple because they only require that one step. So why would these problems be difficult? Well, let's take a look at the problem space for an insight problem. And what does that look like? And non-insight problems, they got problem spaces that look like this. And this is the reason why, as you work on a 9-insight problem, as you work with something like the Tower of Hanoi or the Orcs and Hobbits problem, you know that you're getting closer to your solution. You feel like you're moving through the problem space because there's space to move through this problem space. There's intermediate states that you can go to and recognize that you are no longer in your initial state and you're closer to your goal state. So this is a non-insight problem space. Insight problem spaces, on the other hand, look very different. They look more like this, where you have a start state and you have a goal state and you don't have any intermediate states, but you have a multitude of potential operators that can operate on that start state, but do not get you to the goal state. So when we were trying to go through all of these possibilities, all of these solutions, the haystack was important because the cloth ripped. Each of these lines here represents one of the suggestions that people made. Oh, the haystack is important because the cloth ripped, because this family sells cloth and hay in order to provide food for their family, and the cloth ripped, so now the hay became very important, otherwise they would starve during the winter. Nope, that's not where the goal is. The cloth was carrying puppies, and the puppies fell out and they were going to get injured, but they fell into the haystack. No, not why it was important. Any sort of speculation is probably going to be one of these multitude of operators that do not lead to the goal state. And there's only one that leads to the goal state. So not only when you're trying to solve this funeral problem, why did she kill her sister? Not only are there a multitude of possibilities, you're looking for this one path amongst an almost infinite set of possibilities. So the chance that you're going to start at the start state and make it to the goal state is very, very low. More likely, you're going to end up at one of these red dead end states, one of these red non-goal states, non-solutions to the problem. And worse than that, once you get to that incorrect solution, where do you have to go in order to try to solve the problem? Mm-hmm. You got to go back to the original start state. And as we just saw with backup avoidance, that is something that we are not wanting to do. That is something that we do not do easily. That is something that we try to avoid as much as we possibly can. And that's one of the reasons why these insight problems get frustrating. Because not only did you not get the solution, but you're no closer to the solution, and now you got to back up. You got to undo that operator and go back to the start state and try again. And chances are you're going to try again, get it wrong. Now you got to back up again. Try again, get it wrong. Now you got to back up again. And that violates that idea of backup avoidance. So again, insight problems, they got one step. The challenge is that because of the problem space, that one step is hidden amongst a multitude of steps. So to find that one step is very, very difficult. And again, you have to back up and start at the beginning every single time that you fail. All right, so that was problem solving and creativity. Any questions on that before we wrap this up and start at judgments, decision making, and rationality? All right.